Hi, this is the exercise we were working on last time we were in class. I asked you to imagine a small population of 5 people. Just it could just be any 5 people who have something in common with each other, such as a family of 5 people, maybe. And we sorted out this population into all possible samples of 2 people, meaning all possible pairs of 2 people. And I did sort these out in front of the class. The way I did it is I paired 20 with 22, 20 with 24, 20 with 26, and 20 with 28. And that became the first 4 samples. After I was finished with 20, I moved down to 22, and I paired 22 with all numbers under 22, which became 22 and 24, 22 and 26, and 22 and 28. So I paired 20 with all numbers under 20, and then I moved down to 22, and I paired 22 with all numbers under 22. Then I moved down to 24, and I paired 24 with all numbers under 24, which meant the 2 samples were 24, 26, and 24, 28. There were these two right here. And then 26 could only be paired with 28, because 28 is the only number under 26. So that was the last sample right here. I already calculated the mean and the standard deviation for you. The mean was pretty easy to find. We just had to add up the 5 numbers and divide by 5. The standard deviation I found with Excel, but if I wanted to find it by hand, I would just have to subtract each number by the mean of 24 and then get the deviations and the squared deviations. What we did first is we found the middle 8 samples. What I mean is we found the 8 samples in the center. Actually, that was actually my first question, was what are the 2 boundary points of the middle 8 samples? Let me put that question on here. What 2 sample means are at the boundaries of the middle 80% of the possible samples. It says 80%, but since I gave you 10 samples, 80% just means 8 out of 10. If I give you 10 samples, then 80% means 8 out of 10, 70% means 7 out of 10. So let's actually find the middle 8. They go from here, sample 2, all the way up to sample 9, because there's 1, 2, 3, 4, 5, 6, 7, 8 samples in there. So it looks like the 2 means that are at the boundaries of the middle 80% are 22 and 26. Now if I had said 70% of the possible samples, well, 70% actually wouldn't work. 60% would work, because 60% of 10 is 6 out of 10, so you would just find the middle 6, and that would be 1, 2, 3, 4, 5, 6. The boundaries would be at these 2 points if I asked you for the middle 60%, because 1, 2, 3, 4, 5, 6 samples are in there. But I asked you for the middle 80%, which meant 8 out of 10. So the two answers are just 22 and 26. What if I asked you, what is the 80% margin of error? Before we can find the 80% margin of error, we have to know what the boundaries are of the middle 80%. And we know that they're 22 and 26. What you can do now is take the population mean, which came out to 24, and find how far away that population mean of 24 is from these two boundaries. So the 80% margin of error is just the distance from the population mean to the two boundary points of the middle 80%. This is our population mean of 24. Sample 6 has a mean equal to the population mean of 24. So this is where the population mean of 24 is. If you want to find the margin of error, you could take the population mean of 24 and subtract it by the lower boundary of the middle 80%. So the population mean minus the mean of the lowest sample at the lower boundary of the middle 80% gives you the 80% margin of error. Let's do that. Let's subtract the population mean of 24 by the lower boundary of 22. (24 minus 22 equals 2). Looks like 2 actually is the margin of error. All this 2 really means is that the distance from 24 to 22 is 2. It's just the distance from the population mean to epicenter to the lower boundary of the middle 80%. It's also the distance from the population mean of 24 to the upper boundary, which was at 26. And the reason why this is called the 80% margin of error is basically just because these two boundaries mark off the middle 80%. If these two boundaries marked off the middle 60%, this distance here and this distance here would be called the 60% margin of error. So our answer is 2. Okay. If we take we can create something called a confidence interval. I'll explain what that means. Take the mean of one of the possible samples and create a confidence interval around it. All we have to do is take one of these samples, take its mean, which is a sample mean, and add and subtract the margin of error to the mean of the sample. I decided to work with sample 3. So 23 plus or minus 2. 23 plus 2 is 25. And 23 minus 2 is 21. (21 to 25). Our confidence interval is 21 to 25. Confidence interval is really just the range, meaning the interval between those two numbers. Goes from 21 to 25. And notice how when we created our confidence interval, we took the mean of sample 3 and we added and subtracted the 80% margin of error, which we found out was 2. If we're adding and subtracting the 80% margin of error, the confidence interval is called an 80% confidence interval. So I could say right here, the 80% confidence interval goes from 21 to 25. The reason why it's called an 80% confidence interval is just because we used the 80% margin of error. I'll write this confidence interval under here because it's a confidence interval that was created with sample 3. What if we did it with sample 1, which is outside of the middle 80%? If we made it an 80% confidence interval, it would go from 19 to 23, because we're taking 21 and adding and subtracting 2. If we take sample 10, which is above the middle 80%, and we add and subtract 2 from 27, we get a confidence interval of 25 to 27. Notice how the confidence interval that we created with sample 1 didn't include the population mean of 24, and the confidence interval we created with the highest sample also didn't include the population mean of 24, but the sample that we used in the middle 80% gave us a confidence interval right here that did include 24. So if you want to create an 80% confidence interval by adding and subtracting the 80% margin of error, it'll only include the population mean if you use one of the center 80%, one from the center area, and it won't include the population mean if you use a sample outside of the middle 80%. So think of it this way. You add and subtract the 80% margin of error, you get an 80% confidence interval, and that confidence interval will only include the population mean if the sample came from the middle 80%. Okay. What if, way back at question 1, I didn't say the middle 80%, but I said, what two samples are at the boundaries of the middle 60% of the possible samples? Well, since we have 10 numbers, the middle 60% is just the middle 6. That goes from the lowest one is sample 3, the highest one is sample 8, because there's 1, 2, 3, 4, 5, 6 in the middle. The way I think about it is, if there's 6 inside of here, there's 4 that aren't inside of there, which would mean 2 below down here and 2 above up here, and then 6 would be in the middle, and this would be the middle 6. Okay, so the boundaries of the middle 60%, meaning the middle 6, are 23 and 25. How far is this lower boundary right here of the middle 6 sample of the samples from the population mean of 24? Well, we could do the same thing again. We could take 24 and subtract 23. We could take the population mean and subtract it by the lower boundary, and 24 minus 23 is 1. So if I asked you, what are the boundaries of the middle 60%, you would say 23 and 25. And if I asked you, what's the 60% margin of error, you would say 1. The 60% margin of error is just the distance from the population mean to each of the two boundaries of the middle 60%. So now you know how to do the problem if I said 60% instead of 80%. What if I said take one of the possible samples and create a confidence interval around it? We could take one of these samples and add and subtract the 60% margin of error to create a confidence interval. For example, right here we could add and subtract 1, and we would get a confidence interval of 22 to 24. We just take the sample mean, add and subtract the margin of error. Notice how we're adding and subtracting the 60% margin of error. Since we're doing that, it becomes something called the 60% confidence interval. So the 60% confidence interval goes from 22 to 24. We're doing 23 plus or minus 1. And this is the 60% margin of error. You can try doing this yourself. You can try taking one of the samples that are below the middle 60% and using it to create a confidence interval. You can take one of the samples from the middle 60% like I did and create the confidence interval, and take one of the two that are above the middle 60% and create a confidence interval. And you'll notice that only the ones in the middle 60% include the population mean of 24. Let's look at an example. What if I used 22 right here, which is below the middle 60%? The 60% confidence interval goes from 21 to 23 when I'm adding and subtracting the 60% margin of error. It doesn't include the population mean of 24. We already did this with sample 5, which is in the middle 60% in the blue area. What if we do it with 26 that's out here above this blue area, above the middle 60%? We get, if we add and subtract 1, we get 25 to 27. So these are all 60% confidence intervals because they were all created by adding and subtracting the 60% margin of error of 1. When we did it with a sample below the middle 60%, right here, the 60% confidence interval did not include the population mean. This 60% confidence interval did include the population mean. This 60% confidence interval up here did not include the population mean. So if you're creating an 80% confidence interval, you have to choose a sample from the middle 80% for the confidence interval to go across the population mean. If you're creating a 60% confidence interval, you have to select one of the middle 60% to make the confidence interval go across the population mean. Also notice how when the 80% confidence intervals are always wider than the 60% confidence intervals, because when we were adding and subtracting 2 to create the 80% confidence intervals, we ended up with confidence intervals that had a span of 4 numbers. Like this became 19 to 23 by adding and subtracting 2. That's a span of 4 numbers. When you take a sample mean and add and subtract 1, like we did here, you get a confidence interval that only has a span of 2 numbers, like 21 to 23, which is narrower. So when you add and subtract a smaller margin of error, you get a narrower confidence interval. Now let's see if we can use a z-score to actually give us a formula that can actually give us the margin of error that we already found. Let's see if we can use a z-score to get this margin of error of 2. In order to do that, we have to look at this sample at the upper boundary of the middle 80%, which was sample 9. And we have to create a z-score for sample 9 at the upper boundary. Well, a z-score for a sample is just the sample mean of 26 minus the population mean of 24. You have sample mean minus population mean on top. You have population standard deviation on the bottom. Over the square root of the sample size. All of these samples have a sample size of 2 because they're 2 numbers. So the square root of the sample size goes right here. If you take this, well, first let's find out what this z-score actually is. The square root of 2 is 1.41. If I divide 2.83 by 1.41, I get 2. Looks like I'm getting 2 on the bottom. Okay. I'm not quite sure if that's correct, but we'll see if it is. The top is 26 minus 24, which is 2. This comes out to 1. I'm going to double check my work on the bottom again. Looks like it does come out to 1. What we can do now is we can take this value and it becomes something called our confidence coefficient. The z-score at the upper boundary of the middle 80% of the samples is called the 80% confidence coefficient. I'll just put 80% CC. This z-score of 1 is our 80% confidence coefficient. How can we take the confidence coefficient and get the margin of error? It turns out that you can get the 80% margin of error by multiplying the 80% confidence coefficient by the bottom of the z-score that was actually used to calculate this formula. I mean, you can take the bottom of the z-score and multiply it by the confidence coefficient, and you actually get the margin of error. I'm going to try to explain why this is the case. Notice how when you subtract on top, you get 2. So actually, the top of the formula up here gives us our margin of error of 2. The margin of error is just 26 at the upper boundary minus the population mean of 24. So that is the 80% margin of error. But if we take our confidence coefficient and multiply it by the bottom of the z-score, which was the population standard deviation over the square root of the sample size of 2, this will have to come out to 2. What we're really doing when we do this to get this formula for the margin of error is we're taking this z-score formula that we used, we're multiplying both sides by the bottom of the z-score. I'm running out of space over here. This this came out to be a mess, so I'm going to erase this. Maybe I should start a new page. All I'm trying to do is show you how I was able to get this formula that would give me the margin of error of 2. This whole thing came out to be 1. So 1 actually is z. One actually is the z-score that we found, and it because all of this came out to 1. If you take, and we said it was the confidence coefficient because it was the z-score of sample 9 at the um, upper boundary of the middle 80%. This all cancels out, and we're left with 2 over here. So it turns out that multiplying this the confidence coefficient of 1 by this over here gives us our margin of error of 2. You can try it on your own to find out that it works, and you'll see that this does come out to 2. So if you want to get an 80% margin of error, you could multiply the 80% confidence coefficient the z-score at the upper boundary up here by the population standard deviation over the square root of the sample size of n. If you multiply the 80% confidence coefficient by this fraction right here, you get the 80% margin of error. Now, what if I wanted to use this same formula to not get the 2 margin of error, but to get the 1 margin of error, which went along with the middle 60%? Well, we would do the same thing. We would still get the z-score of the upper boundary, but this time the upper boundary is here because we're dealing with the 60%. And the boundary is the sample 8, which has a mean of 25. You would take 25 minus 24. It's the mean of the sample minus the population mean again over the population standard deviation over the square root of 2. said that the z-score at the upper boundary is called the confidence coefficient, and this was called an 80% confidence coefficient because it was at the boundary of the upper boundary of the middle 80%. We're once again finding a z-score at the upper boundary, but this time it's at the upper boundary of the middle 60%. So this z-score will be called a 60% confidence coefficient. Let's see what it comes out to. I took a little bit of a shortcut, but this z-score comes out to 0.5. The z-score of sample 8 comes out to 0.5. So 0.5 is the 60% confidence coefficient because it's the z-score at the upper end of the middle 60%. If we substitute the 80% confidence coefficient for our 60% confidence coefficient, and we keep these values here, it will actually give us an answer of 1, which is the 60% margin of error that we had at the beginning. So we found the margin of error of 2 and the margin of error of 1 easily at the beginning by just looking at the samples. All I showed you now is just kind of a long way of reaching the same answer by getting a z-score and then doing some algebra and then changing the z-score to the margin of error. And the whole point of this was just to show that you don't have, if you didn't want to, I guess if you wanted to do this the hard way, there is a formula that could give you the margin of error. It can be done with a formula. So to get your margin of error, you take the correct confidence coefficient with the right percentage, multiply it by this fraction right here, population standard deviation over square root of sample size, and you get the margin of error that you wanted. And on your own, what you could try is actually getting this z-score and seeing that it does come out to 0.5, and then actually taking 0.5 and then multiplying it by this, and then seeing that it actually does work and it actually does give you the margin of error. Now, how would we create a confidence interval if we were taking a sample from a large population? For example, we take a sample of 40 people from a population of college students in the Bay Area, and we calculate the mean GPA of our sample. We want to create a, let's say, 80% confidence interval around the mean of our sample. Remember how if you have the mean of a sample, you can create a confidence interval around it. Just now, instead of it being a sample of 2 people, we're dealing with a sample of 40 people. And it's a sample from a much bigger population. we need to look at the confidence interval formula. I think this formula will make sense after the work that we've already done. First, let's look at it in words. Sample mean plus or minus margin of error. Since we want an 80% confidence interval, it'll have to be the 80% margin of error, because remember before, when we created an 80% confidence interval, we took the 80% margin of error of 2, and we added and subtracted that to the mean of the sample. We found a formula for our margin of error, which was the confidence coefficient times the population standard deviation over the square root of the sample size. Because from our formula we found out that this is the margin of error. So now, well, we realized if we plug in the right coefficient and we multiply it, we'll get our margin of error, because back here, when we did it, we plugged in the 80% confidence coefficient, and we ended up with our margin of error of 2. So this formula, we know it does work. The way this is written out in symbols is the confidence coefficient is Z with the Greek symbol. It's actually alpha over 2 times the population standard deviation is this symbol, the sigma. This is over the square root of the sample size. This whole thing is the margin of error, just in symbols instead of words. Now, how do we do this? Well, first we have to know what the mean of our sample is. Let's say it comes out to an average GP of 2.8. Our sample mean is 2.8 now. What about the population standard deviation and the sample size? Well, we'll worry about that later. We need to get our confidence coefficient. If we want the 80% margin of error, we need the 80% confidence coefficient, which is the z-score at the upper boundary. Remember, the z-score at the upper boundary of the middle 80%, which was right here, was our 80% confidence coefficient, and it turned out to be 1. Now, how do we do this when we don't actually have those possible samples in front of us? Well, there's something we can do. You know, we took a sample of 40 people from a big population. It turns out that when you do that, when you take a sample of at least 30, the possible samples that you're drawing from roughly follow a normal curve like this. we didn't have a normal curve over here, because if we plotted these samples out, it would have been 21 would have been down here, 22 would have been here. We had two 23s. I think we had two 24s and two 25s. And we had a 26 and a 27. I'm not really, this isn't actually part of the problem. I'm just trying to make a little bit of a point here. Well, it's not quite a normal shape. But if over here, since we have a sample of at least 40, it does follow a normal shape, which means that the confidence coefficient, which is the z-score at this upper boundary of the middle 80% of samples, can actually be found. It can actually be looked up in a table, even though we haven't listed out all of the possible samples that we're drawing from. We can actually look up this confidence coefficient in a table and find out what it equals. We can use a normal curve table. So let's go to our z-table. What we can do is, we know that in this table, these decimals are meant to be the percentage of the normal curve that's below or to the left of a certain z-score. We want our 80% confidence coefficient up here. Now, what's the total percentage that's below our sample meaning? Below our z-score, which is here, and all the way to the left. What you have to do is, if I tell you it's an 80% confidence interval, create a curve like this, mark off the middle 80%, and then subtract 100 minus 80, and you get 20. Divide that by 2, split it in half, and you get 10, which means that since 80% are in the middle, this tail here has to be 10% of the samples, and this has to be 10% up here. Because they all have to add up to 100. So what we really have is just our lower tail, the lower 10%, the middle 80%, and the upper 10%. It's really just the same thing we had back here with the lower. This was a lower 10%. This was the middle 80%, and this was sample 10 was the upper 10%. We had a lower tail, a center 80%, and an upper 10%. The only difference now is that we're drawing from many more samples, and we know that they follow a normal curve. These mean the exact same thing. It's a lower tail, a center, and an upper tail. Now what percentage of the curve is all the way to the left of this confidence coefficient. Well, if you add the middle to the lower tail, you get 90%. You combine them, so 90% of the samples are below the confidence coefficient that we're dealing with. So why is this important? Well, once we do this, we can go to our z-table, standard normal table, find the decimal inside of here closest to 0.9. So here we have 0.9032. Right here we have 0.0997 and 0.9015. Which one is closest to 0.9? Well, let's see. We can just take 0.90 and subtract it right here. Comes out to 0.0003. Turns out that this one is actually closer. I'll probably explain to you somewhere else outside this video why this one is the closer one. But for right now, just realize that we needed to get the closest one to 0.9 because 90% is 0.9. What we do now is we go back to the row, find out what row it's in. It's 1.2. We go up to the column and it's 0.08. What we have to do is we have to put these together. We have to take the row of number of 1.2 and combine it with the column. It's 0.08. If you put them together, you just take the 1.2 and add the 8 to the end. This last part, the first part's the row, the second part is the column. A row and column. That gives us this right here, confidence coefficient. And then well, this is the population standard deviation. We have our sample mean. We have our confidence coefficient, which came from the table. The population standard deviation would have to somehow be known. But if I say that the population standard deviation is somehow known to be 2.8, we don't know what it is because we're taking a sample from a very big population and we don't know what its standard deviation is. What's our sample size? We're creating a confidence interval with a sample size of 40. It's a sample of 40 people because this was the mean of a sample of 40 people. So it's a sample size of 40, actually. So pretty much all you have to do is just plug in these values. Well, the sample mean, the population standard deviation, and the sample size are the easiest parts because these are usually given to you inside of the question, and you just plug them in like I did here. But the difficult part is finding the fourth value, which is this confidence coefficient. What you have to do to get that is you have to look at what percentage I'm telling you. I said 80% confidence interval. Because I said that, create this normal curve, mark off the center 80%, find out what percentages the tails are by taking 100, subtracting the percentage I gave you, which in this case is 100 minus 80, and it came out to 20. This is just 100 minus the percentage I gave you. Take your answer and divide it by 2, and you get a number. This number is your tails. We got tails of 10 and 10, because the entire thing has to be 100%. So if the middle is 80, the two tails are 10 and 10, because these three numbers all add up to 100. You then take the center percentage, which is actually what I gave you, add it to the lower tail percentage, and in this case, 80 plus 10 came out to 90. What you do now is, since it's 90% total to the left, take the 90%, change it to a decimal, and then go to the table like I showed you, and then get the z-score, and that becomes the confidence coefficient. So if I take the 0.90 to the table gives me this, the 1.28. Then the confidence interval is just all of this multiplied out. You can check me on this. I think this entire part right here comes out to 0.5, about 0.57 when you calculate all of this, which would mean now, to get the confidence interval, we would just add and subtract this to get two numbers. Remember, confidence interval is adding and subtracting two numbers. We get 2.23. If we add, we get 3.37. So our confidence interval goes from this to this. We've created an 80% confidence interval around our sample, which is what we were doing at the beginning of this video, except now we actually did it with a formula and a table instead of just doing it, well, with our list of samples that were listed out. So whenever you're taking a sample from a population, like right here, we were taking a sample from a small population, you have a margin of error, and you can add and subtract that margin of error to get a confidence interval, like we did here. If you're taking a sample from a much bigger population, such as from a population much bigger than 5 people, you actually don't have all of the possible samples listed out for you, you actually can still get the margin of error. Because here we got the margin of error by just drawing this line and adding and subtracting. But we can take this formula, get our margin of error, add and subtract, and then get a confidence interval. And the purpose of doing this in real life is to actually try to estimate what the unknown mean of a large population is. What we're hoping is that we're hoping that if we can somehow get a sample from the middle of the possible samples that we're drawing from, we'll end up creating a confidence interval that goes across the population mean. And we'll be able to capture the population mean inside of our confidence interval. So it's a way of estimating the population mean by creating an interval or a span of numbers that the population mean should fall inside of. And the idea is, as long as you get a sample from the middle section, the confidence interval will work, and it will have your unknown population mean inside of it. So in real life, it's just a way of using a sample to estimate the mean amount of something of an entire category or population of people. And you might be wondering, how would this be done if population standard deviation hasn't been calculated? Well, what you can do is take the people in your sample, calculate a standard deviation for those people only. It becomes a sample standard deviation. Substitute that for the population standard deviation in the formula. And it should be close enough. I mean, the sample standard deviation should work fairly well as a substitute. And you can then calculate your confidence interval that way. And that's pretty much how it would be done in a real life study.